Hi guys, welcome back to our discussion on phase equilibrium. So today we'll be focusing on multi-component condensed phase equilibrium as a continuation of our previous discussion on the general thermodynamics of phase equilibrium and our introduction to the Gibbs phase rule. Okay, so today we'll focus on how to construct and interpret phase diagrams, so get your sketching skills ready. Okay, so for our discussion, we'll be looking at general cases of two-component and three-component condensed phase equilibria. For two-component systems, we'll focus on a system in which we have complete miscibility in the liquid phase as an example case. And for three-component systems, we'll look at when all the components are liquids and when we have two solids in one solvent system. Okay, keep in mind, however, that there are many other possible cases of multi-component systems, but for the sake of our introductory discussion, we'll just limit our discussion to a few examples so we could just get a grasp on how to work with multi-component phase diagrams. Okay, so to start off, let's look at our two-component system. Okay, so for our two-component system, we'll consider the case in which we have complete miscibility in the liquid phase. That is, if we mix together the two liquids A and B, they will form a homogeneous liquid mixture in all proportions. Okay, an example of a completely miscible liquid system is ethanol and water. Okay, so if we lower the temperature of this liquid mixture, we expect that the liquid mixture will just freeze together, forming a solid with both A and B crystals. Okay, however, a sort of evenly distributed solid is not always achieved. Okay, in fact, depending on the composition and the melting temperature of the components will tend to solidify into their pure solids, forming larger crystals of their corresponding solid first before the other component solidifies. Okay, so for example, if we have more A in the solution, A tends to crystallize out of the solution first, followed by B. Okay, otherwise, if we have more B in the solution, B tends to crystallize out of the solution first, followed by A. Okay, so this type of freezing melting behavior has many practical applications. One is fractional freezing, in which we can purify liquid-liquid mixtures by selectively freezing out certain components. This is sometimes used to increase the alcohol content of alcoholic beverages by freezing, since alcohol doesn't freeze evenly. Okay, so ice freezes out first, making the solution richer in ethanol. Okay, so another application is probably more familiar to you guys, the purity determination of solids by changes in melting point. Okay, so as you know from your laboratory classes, when a solid has an impurity, its melting temperature tends to decrease due to the disruption of its crystal lattice with the impurity. Okay, so another application is so-called deep eutectic solvents, which are liquid mixtures of two components that has a melting temperature much lower than those of the pure components. Okay, so we'll see how this forms when we discuss the phase diagram. Okay, so in constructing our phase diagram, we'll consider two major cases. Okay, so the first case is the simplest. We'll look at the case when our two components just mix together and there are no chemical reactions between the two. Okay, so the second case is when it's possible to have a chemical reaction between the two components. Okay, so we'll look at two types of possible reactions. Okay, the eutectic and the peritectic reaction. Okay, so as a reminder, it may seem like we're looking at so many different phase diagrams, but just keep in mind that many of the principles that will apply for the simplest case, which is the first case we'll discuss, will also apply for the other cases. So we'll discuss the first case in detail and we'll quickly go over the other cases and see what's different about them. Okay, so before we start, let's look at applying the Gibbs phase rule for our two-component systems for condensed phase equilibrium. Okay, so our general equation for the Gibbs phase rule is F is equal to 2 plus C minus P. Okay, so since we have a two-component system, C in this case is going to be equal to 2. Okay, so in general, we have the Gibbs phase rule as F is equal to 4 minus P. Okay, so since we have at least one phase, okay, so if we have one phase, F is going to be equal to 4 minus 1, so this is going to be equal to 3. Okay, so the type of variables that we have to specify then would be temperature, pressure and composition, okay, so percent composition, okay. In most cases of condensed phase equilibria, however, we don't really see significant changes in pressure, so typically we just consider variations in temperature and composition, okay. So typically we set pressure conditions as constant. Okay, so if we have constant pressure conditions, okay, we could treat one of the variables here in the two-part here as constant. So our Gibbs phase rule just becomes F is equal to 1 plus 2 for two components minus P. So overall, F is going to be equal to 3 minus P for our two-component system if we hold our pressure constant. Okay, so for the most part, then we'll be looking at temperature and composition phase diagrams. Okay, so here is our temperature versus composition phase diagram. So again, pressure is held constant. Okay, so in this particular diagram, we have mole percent B as the x-axis. So for emphasis, we'll indicate that on the right side here, we have 100% B and 0% A. Okay, so overall, this borderline over here, this represents pure B. Okay, also for emphasis, since we have a two-component system, keep in mind that 100% minus mole percent B will give us mole percent A. Okay, so in this direction, in this opposite direction, we have mole percent A. Okay, so while we have 0% A on this side, we have 100% A on this side and 0% B on this left side. Okay, so overall on this borderline here, we have pure A. Okay, so on the y-axis we have temperature. Okay, so since we're dealing with solid-liquid equilibrium, we should indicate the melting temperatures of A and B. So in this example, let's have a higher melting temperature for A. Let's also indicate the melting temperature of B over here. Okay, so if we start to move towards the right, we're adding small amounts of B to our pure A. Okay, so recall again what we know about the addition of impurities to the pure solid. Okay, so we tend to decrease its melting temperature, so overall we can draw a melting curve that tends to decrease as we add more B to our solution. Okay, so let's draw that curve over here. Okay, so there we go, it's sloping downwards. Okay, so the same thing can go for B. Okay, so we now have two curves that meet at a certain point here. Okay, so this intersection here, this is called the eutectic point. Okay, so this point corresponds to the composition of the mixture that has the lowest melting temperature. Okay, so below this temperature, the solution just solidifies all in all. Okay, so at this intersection, this is the lowest temperature at which we'll observe a so-called melt. Okay, so the melt is just a liquid mixture of the two components. Okay, so below this temperature, the temperature is low enough just to cause the entire mixture to just freeze or solidify. Okay, so to complete our phase diagram, we'll label each of these regions with the corresponding phases that exist at those points. Okay, so we'll also label it with the corresponding variances. Okay, so at this region above the melting curves, we expect to see a melt. Okay, which again is what we usually call the homogeneous liquid mixture of the components A and B. Okay, so since we have a single phase, a homogeneous liquid mixture, P is equal to 1. Okay, so keep in mind again that our expression for variance is just 3 minus P. Okay, so since P is equal to 1, our F is going to be equal to 2. Okay, so the parameters that we need to specify include temperature and composition in order to describe the system. Okay, so inside here, we could determine the phases that exist just by looking at the bordering lines. Okay, so on the left side here, we have pure A, and on the right side here, we have the melt. Okay, so we know that the phases inside this region here are pure solid A and the melt. Okay, so we have two phases here. We have a solid, we have the liquid. Okay, so P is equal to 2. So our variance is going to be equal to 3 minus 2. So that is just equal to 1. Okay, so the same analysis could go for this region over here. Okay, so we have pure B on this side here. We have the melt over here. So that means we have solid B and the melt. Okay, so below this eutectic temperature, we just have a mixture of A and B in the solid form. Okay, so in this case we have two phases, okay, so A solid and B solid, so that means our variance is also going to be equal to 1. Okay, so how about for the eutectic point? Okay, so at this point we actually have a melt in equilibrium with the solid mixture of A and B. Okay, so the number of phases is equal to 3. Okay, so 3 meaning the melt and the pure solid A and pure solid B. Okay, so that means our variance, which is equal to 3 minus P, is just going to be equal to 0. Okay, so the eutectic point is considered to be an invariant point. Okay, so this is going to be characteristic for our mixture. Okay, so overall, now we just addressed the question of what phases are present during which temperature and composition conditions. Okay, so we still have to answer questions that address what are the compositions of our phases. Okay, so for example, if we're in this region over here, how do we determine the composition of the melt? Okay, and we also want to know if temperature changes, how does the composition of the two phases vary? Okay, so to make this clear, let's look at an example mixture. Okay, so let's say that we start with a liquid mixture that is 85% A and 15% B. Okay, so we'll start at this high temperature over here. Okay, so initially we have again a homogeneous liquid mixture of A and B. Okay, so as we decrease the temperature to below the melting line, we see that we have A solid and melt. Okay, so keep in mind, however, that overall, the composition of the mixture is still 85% A and 15% B. Okay, so that means that since some of the A moved out of the melt to crystallize, the composition of the melt at point 1 and point 2 are going to be different. Okay, so more specifically, the melt at this point here will have less A since A moved out of the solution to crystallize. Okay, so just always keep in mind the conservation of mass principle. Okay, so again, this freezing behavior is very useful for purification purposes. Okay, so we could see that we could filter out the crystallized A in order to separate it from component B. Okay, so this is what happens with fractional freezing of alcoholic beverages. Okay, so in that case, pure water freezes out, so we could decrease the concentration of water and therefore increase the concentration of ethanol in the liquid solution. Okay, so as we decrease the temperature further, note that more A crystallizes out of the solution. Okay, so the composition of the melt also changes as we have even less A in the melt compared to the composition of A in the melt at point 2. Okay, so once we decrease the temperature to the eutectic temperature, this is when most of the melt starts to freeze. Okay, so note that the composition of the melt at this point is now the eutectic composition. So this point also corresponds to the maximum amount of A that we could purify from the original solution. Okay, so just before the rest of the melt freezes, for example, we could separate out the solid A. Note that it's not possible to completely separate A from B by freezing it out, since once we reach the eutectic temperature, okay, B also starts to freeze alongside A. Okay, so overall, once we decrease the temperature below the eutectic temperature, nothing really changes in the composition of the phases in the system because all of A and B are already frozen. Okay, so just by decreasing the temperature, we're pretty much just cooling the solid. Okay, so now that we have a much clearer image of what's happening throughout the phase diagram, now let's look at how we could use the phase diagram to also determine the composition of each of the phases. Okay, so this is especially important in the A solid plus melt region, where we saw earlier that we have changes in composition of the melt as A crystallizes out of the solution. Okay, so we'll investigate what happens at temperature 1 and temperature 2 indicated here. Okay, so we can determine the composition of the melt by drawing so-called tie lines. Okay, so these are horizontal lines originating from the composition and temperature of interest that intersect the phase boundaries. Okay, so in this case, we are intersecting the A-solid boundary and the melting curve. Okay, so the intersections of the tie lines tells us what phases are present again. So we have A-solid here and the melt here, and it also tells us the composition of those phases. Okay, so what's most useful here is the composition of the melt. Okay, so if we draw a vertical line from the tie line's intersection at the melting curve at T1, we can determine the composition of the melt as 60% A and 40% B. Okay, so note that this is consistent with our earlier analysis. Okay, so if we have a solution that is originally 85% A and 15% B, and some of the A crystallizes out of the solution, the melt will decrease in amount of A and will appear to be more concentrated in B. Okay, so we can also draw a tie line at temperature 2. Okay, so drawing a tie line to the melting curve shows us that the composition of the melt is now 45% A and 55% B. Okay, so again, consistent with our earlier analysis, more A moved out of the melt, therefore decreasing the concentration of A in the solution and increasing the concentration of B. So now that we know the composition of the phases and the way that the composition might change with temperature, so we can now address a more practical question on how the entire mixture distributes itself amongst the phases. Okay, so for example, we might be interested in knowing how much of the mixture at a certain temperature will move into the pure A phase, or how much of the mixture will move towards the melt. Okay, so an example question that we might consider is if we're given a total amount of solution. Okay, so in this case, say that we have 10 moles of solution. Okay, so the question might be how many moles of pure A might crystallize at temperature 1 and temperature 2. Okay, so note that what we know at this point is that 85% of 10 moles is component A. So we have 8.5 moles of A and 1.5 mole of B. Okay, so we also just know the composition of the phases, but not how much of the original mixture is actually in those phases. Like we don't know the exact amount of how much of the solutions, 8.5 moles of A, that is in the solid phase and how much remains in the melt. So always keep in mind, however, that when we're going down in temperature, we still have the same overall composition. Okay, so we're just changing how the solution gets distributed between the phases. Okay, so we always have to keep in mind the law of conservation of mass. Okay, so a nice graphical method that we could use to help us determine the distribution of the mixture between the phases is the lever rule. Okay, so this technique is actually applicable to any composition phase diagram. So what we'll discuss here can also be used later on for other phase diagrams. Okay, so the lever rule, as the name suggests, is based on the concept of a balance lever. Okay, so consider this picture of a lever here. Note that in order to balance the lever, the heavier weight, which is this over here, should be closer to the pivot point, whereas the lighter weight must be farther. Okay, so the relationship of mass and distance to the pivot point is inversely proportional. So in the application of our lever to our system, the masses on the lever can correspond to the mass or moles of the solution in one phase and the moles of the solution in another phase. Okay, so we have N1 here and N2 over here. Okay, so let's also label the corresponding distances of the weights from the pivot points of the lever. Okay, so we have D1 here and we have D2 over here. Okay, so the relationship between the number of moles of each weight and the distance of the balance lever will be given as N1 times D1 is equal to N2 times D2. Okay, so note that in terms of direct proportionality, the heavier weight N1 is going to be proportional to the opposite distance. Okay, so N1 will be directly proportional to D2. Okay, and we also have the corresponding relationship of N2 and D1. Okay, so the smaller weight will be directly proportional to the smaller distance, which is the opposite side. Okay, so taken all together, we can note that the sum of the amount of matter, N1 plus N2 will be proportional to the sum of the distances on the lever, okay? So overall, N1 plus N2 is directly proportional to D1 plus D2, okay? So these distance relationships will allow us to calculate a mole fraction of the number of moles of solution in one phase and the other, okay? So for example, okay, so the mole fraction of the mixture in phase 1 is going to be expressed as, okay, so it's just N1 over the total number of moles, right? So N1 plus N2, okay? So in terms of distances, okay, we could express this as, since N1 is directly proportional to D2, okay, this is going to be D2 over the total distance, okay? So D1 plus D2. Okay, so overall, the mole fraction of our overall mixture that is in phase 1 is going to be equal to D2, which is the opposite distance over the total distance. Okay, so the same thing can go for the mole fraction of our solution in phase 2. Okay, so this is going to be equal to N2 over the total number of moles. Okay, this is going to be equal to D1 over D1 plus D2. Okay, so always just keep in mind that we'll be using the opposite distance in our lever in order to calculate the corresponding mole fraction of a particular phase. Okay, so you might be wondering, what does a lever have anything to do with a phase diagram? Okay, so, well, we could use the concept of a lever to make sure our masses are conserved when we distribute it between the phases. Okay, so in the case of our solution at temperature 1, our pivot point will be this point over here, whereas our lever will be the tie line that connects the phase lines, okay? So we can label D1 as this distance over here and D2 as this distance, okay? So what about our weights, okay? So our weights on this side of the lever will be the number of moles in pure A, and on this side, it will be the number of moles in the melt. Okay, so overall, if we want to calculate the mole fraction of our entire solution, okay, that is in the A solid phase, okay, this is going to be equal to, again, the opposite distance, okay, so that is going to be equal to D2 over D1 plus D2. The mole fraction, on the other hand, of the solution that is in the melt, okay, this will be the opposite distance, okay, so this will be D1 over D1 plus D2, okay? So note that we could actually use the values on the phase diagram as a basis for our distances, okay? So our x-axis here is in terms of mole fraction of B, okay? So we could use the values of B given here in order to determine the distances, okay? So in this case, D1, this is equal to, okay, so it's from 0, the 0 axis, to 15. So D1, this is equal to 15, whereas D2, this will be this particular distance over here, so that will be equal to 40 minus 15, so that is equal to 25, okay? So the total distance over here, this will be equal to 40. Okay, so we could use those values to calculate the corresponding mole fraction. The mole fraction of the solution that is in solid phase A, this is going to be equal to 25 over the total distance, which is equal to 40. So this is equal to 0.625. Okay, so overall the mole fraction that is in pure solid A phase is 0.625. Okay, so in this particular case, if we're calculating the mole fraction of the melt, okay, so we have D1, that's 15, over the total distance, which is equal to 40. So the mole fraction of our solution in the melt is equal to 0.375. Okay, so these are the corresponding mole fractions, okay? So let's apply these mole fractions to our solution that we had earlier, okay? So if we have a total mixture that is made up of 10 moles, okay, that means that if we have mole fraction of A in the solid phase as 0.625, that means for a 10 mole mixture, that means we have 6.25 moles of our solution in A, Okay, so if we're looking at the mole fraction of our melt, this is equal to 0.375. This means that of our 10 moles of solution, 3.75 moles is in the melt. Okay, so we also know the compositions of these phases in terms of how many moles of A and how many moles of B are in the corresponding phases. Okay, so since for this particular phase we're dealing with pure A, we know that 100% of the solution that is in the pure A phase is just going to be A. Okay, so this means that we have 6.25 moles of A that is in the pure A solid phase. Okay, so if we're dealing with a melt, however, okay, we know that we have a composition of both A and B in the melt, okay, at this particular temperature. Okay, so we know that we have 3.75 moles of our solution in the melt. Okay, so this is distributed between A and B. Okay, so we know that our melt is made up of 60% A and it's also made up of 40% B. Okay, so if we get 60% of our mixture, okay, 60% of 3.75 moles, this corresponds to 2.25 moles of A in the melt, okay, and if we calculate 40% B, that is 1.5 moles of B. Okay, so overall, we now know how many moles of our solution are in the corresponding phases. Okay, just to reiterate, we know that if we start with 8.5 moles of A plus 1.5 mole of B in the melt and we decrease the temperature to temperature 1, okay, 6.25 moles of A will move to the solid phase. Okay, so 6.25 moles of A will crystallize out. Okay, so this will leave 2.25 moles of A and 1.5 mole of B in the melt. Okay, so again, this is consistent with our law of conservation of mass. Okay, so keep in mind again that the total number of moles of A is equal to 8.5 moles. Okay, so when we sum up the moles of A that are in the solid phase and the moles of A that are in the melt, okay, so we have 6.25 plus 2.25, that is equal to 8.5 moles of A. Okay, so we only started with 1.5 moles of B, right? Okay, so we could see here that all of the B is still in the melt. Okay, so this is how we could use the lever rule to calculate the number of moles of A and B that are distributed within the different phases. Okay, so we could also do the same analysis for temperature 2. So now we could calculate the number of moles of A that crystallizes out as we decrease the temperature further. Okay, so let's look at our corresponding lever for temperature 2. Okay, so if we're going to calculate the mole fraction of our solution that is in the A solid phase, this will be equal to, again, the opposite distance, so D2 over D1 plus D2. Okay, so again, we could use the different values that we have on our phase diagram to determine what these distances are. Okay, so D1, that is again equal to just 15. Okay, D2, this is equal to this distance again, so we have 55 minus 15, so that is equal to 40. So the total distance here, this is just equal to this value over here, which is 55. Okay, so upon calculating the mole fraction of our solution in the A solid phase, this is going to be equal to 40 over the total distance, 55. Okay, so this gives us 0.727. Okay, so if we calculate the mole fraction of our solution in the melt, okay, this will be D1 over D1 plus D2, so that is equal to 15 over 55, so that is equal to 0.272. Okay, so we can see from comparing this with the distribution of our phases from temperature 1, we could see that more of our solution crystallizes out into the A solid phase. Okay, and then we have less of our solution in the melt. Okay, so if we apply this to our 10 mole solution, we could calculate the number of moles in the A phase and the number of moles in the melt. Okay, so again, recalling the value of the mole fraction of our solution that's in the A phase, this is equal to 0.727. Okay, so considering 10 moles of solution, this gives us 7.27 27 moles that went into the A solid phase, okay? So again, since A solid, this is just 100% A, that means we have 7.27 moles of A that crystallized out of the solution, okay? So if we're interested in what remains in the melt, okay, so let's recall the mole fraction of our solution that's in the melt. So this is equal to 0.272, okay? So this is going to be equal to 2.72 moles of our solution that remains in the melt, okay? So if you want to figure out how many moles of A and B are in this melt over here, okay, let's consider the composition of our melt. Okay, so we know that we have 45% A, okay, so 45% of 2.72 moles, that is equal to 1.22 moles of A, and we also know that we have 55% of B, okay, so that means 55% of 2.72, that is 1.50 moles of B, okay? So always recall again the original composition of our mixture, okay? So for 10 moles of solution at 85% A and 15% B, this tells us we have 8.5 moles of A and 1.5 moles of B, okay? So consistent with this, okay, so all of the B is in the melt, okay? And if we add up the moles of A that got distributed in the solid form and the melt, okay, if we add these two things together, we get 8.5 moles of A, okay? So again, we still have the conservation of mass principle, okay? So just to summarize what happens in the different temperatures, okay, so we're wondering how many moles of A gets to crystallize as we decrease the temperature. So at temperature 1, we saw that we have 6.25 moles of A that crystallized out of solution, okay? So as we decrease the temperature further, we saw that we increased the amount of solid A, okay? So it became 7.27 moles, okay? So note again that we still maintain the original composition of our system, okay? So in both of these cases, we still have overall 85% A and 15% B, okay? So in order to crystallize out A, okay, from the solution, we just decrease the amount of A that's in the melt, okay? So for the melt over here, okay, this is made up of just 2.25 moles of A, and still we have 1.5 moles of B, okay? And in the melt over here, okay, we could see that we have a decreased distribution of A in the melt because most of it froze out. Okay, so we have just 1.22 moles of A in the melt, and again, we still have our B that is in the melt. Okay, so that is how we could use the lever rule to determine the number of moles that gets distributed in each of the phases. Okay. Okay, so here are just some examples of case 1 systems. Okay, so we have several types over here. So we have a metallic system, an ionic compound system, and even a molecular compound system. Okay, so overall, all of these systems follow our simple case 1 phase diagram. Okay, so overall, we could say that our case 1 system is a very universal system. Okay, so it could apply for many types of two-component systems. Okay, so with all the principles that we just discussed, okay, so let's address a very practical problem over here. Okay, so this is a problem that deals with purification. Okay, so as we saw earlier, we were able to purify solid A by decreasing the temperature. Okay, so in this particular problem, we're dealing with a lead and tin system. Okay, so it forms a simple eutectic at 62% by mass tin. Okay, and we're also given the eutectic temperature over here. Okay, so what we're given here is that we start with a 100-gram molten mixture of lead and tin. Okay, that is originally 75% by mass lead, and it's cooled to just above the eutectic temperature. Okay, so it's cooled just before the entire mixture freezes. Okay, so we want to know what maximum mass of lead that can be purified from the molten mixture. Okay, so in order to analyze this problem, it's probably helpful to draw a very quick sketch of the phase diagram. Okay, so note that in this particular example, we're dealing now with by mass as our unit for percent composition. Okay, So here's our basic phase diagram. We have our temperature, okay? And we also have our percent composition. So we could put this in terms of percent tin. Okay, so we know that at 62% tin, so let's just put this over here, 62%, we have our eutectic composition, okay? So we could say here that we have our eutectic temperature, okay? So as a quick sketch, we have our typical shape, okay? So here we have it, okay? So this is our phase diagram. We're going in this direction of percent tin, and we're going in this direction for percent lead, okay? So in our particular example, we start with 100 grams molten mixture of lead and tin. Okay, so we know that we have 75% by mass lead in our original mixture. So that means we have 25% tin. Okay, so let's put this over here, 25% tin, okay? So say that we start over here, okay? So we start with our molten mixture, okay? So eventually what we're doing here is that we're cooling our mixture down. So note here what's going to be the composition of our diagram here. We're going to have lead solid, and we're going to have our melt, okay? So recall again that since we have tin on this side going this direction, we have 0% tin here, therefore we have 100% lead, okay? So this is our pure solid lead here, okay? So previously what we've been doing is that we've been cooling our system to within this region, okay? But note from our earlier analysis that if we cool our system to just above the eutectic temperature, okay, we're going to freeze out the maximum amount of lead that we could crystallize out of our solution, okay? So if we start to cool it below the eutectic temperature, however, note that the rest of the melt is also going to freeze alongside our pure solid lead, okay? So this is like the last chance to purify the most lead that we can, okay? So our corresponding tie lines are going to be here, okay? So our tie line here and our tie line all the way to the eutectic composition, okay? So we already know what the composition of the melt is going to be, and that is going to be the eutectic composition. So that is 62% tin, okay? So here we have our lever. This is our pivot point, okay? So this is going to be D1. This is going to be D2, okay? So now what we're interested in is that we're interested in getting the amount of our solution that went into the lead solid phase, okay? So note, however, that our problem is in terms of mass now, okay? So we could get the mass fraction instead, okay? So mass fraction, this is going to be equal to, okay, so it's just going to be the mass of lead over the total mass. Okay, so this could be expressed in a similar fashion as what we've been doing earlier. So this could be, okay, so opposite distance, okay, so we're dealing with our mass over here of lead, we need to deal with the opposite distance, so this is D2 over D1 plus D2, okay? So our mass fraction, this is going to be equal to, okay, so D2, this is going to be 62 minus 25, okay, and our total distance over here, this is going to be equal to 62, okay? So upon calculation of this, our mass fraction is 0.5967, okay? So this is the mass fraction of our original mixture, 100 gram mixture, that went into the lead solid phase, okay? So since we know that we have 100 grams of our solution, okay, we could calculate the exact mass of our solution that went into the solid phase, okay? So this is 59.67 grams, okay? So this is the amount of our solution that went into the pure solid phase. And since we know that our lead is, of course, 100% lead, okay, so this mass over here, this is equivalent to the lead solid that crystallized out of the solution, okay? So this represents the maximum mass of lead that can be purified from the molten mixture, okay? So keep in mind that our original mixture is 75% by mass lead, okay? So that means the original amount of lead in the entire mixture, okay, this is going to be 75 grams, okay? So that means the remaining amount, okay, so 75 minus 59.67, that is around 15.33 grams of lead. Okay, so this 15.33 grams of lead is still in the melt phase. Okay, so that means we won't be able to crystallize 15.33 grams of our lead because it's still in our melt phase. And if we decrease the temperature to below the eutectic temperature, okay, this amount of lead is going to freeze alongside the remaining tin in the lead as well. Okay, so again, this represents the maximum amount that you could purify for our solution. Okay, so hopefully this problem is clear now. Again, you can see the practical application of using this phase diagram in order to perform fractional freezing. So now that we're familiar with the basic two-component non-reacting system, let's look at cases in which we might see a reaction between our two components. Okay, so in the first such case, let's consider the so-called eutectic reaction, or when we have a so-called congruently melting compound. Okay, so in other words, the compound is stable up to its melting point. Okay, so in our system AB, let's say that we have a compound AB2 that forms. Okay, so our reaction is going to be, okay, so 1 part A, 2 parts B, forming our compound AB2. Okay, so if we have a stoichiometric ratio of 1A and 2B, we have a compound AB2. Okay, so we can calculate where we can plot this compound by computing the molar ratio. Okay, so again, this is made up of 1 mole A, okay, so 2 moles B. Okay, so the total number of moles, this is going to be 3 moles, 3 moles. Okay, so this means that we have 33% mole A and we have 67% mole B. Okay, so that means that we could represent this compound, the formation of this compound, when we have this exact composition in our mixture. Okay, so that is 67% B, 33% A. We form our compound AB2 on our phase diagram. Okay, so to emphasize what we mean by congruently melting compound, okay, so that means when we reach the melting temperature of AB2, okay, so we have AB2 solid, this just forms AB2 liquid, okay? Our compound just melts congruently, okay? If we plot out the melting temperature of AB2, okay, so keep in mind along this composition, we're just going to have AB2 because we just have the right amount of A and B in our mixture. Okay, so we'll have an entire line here that represents solid AB2. Okay, so this maximum over here, this represents the melting temperature of AB2. So beyond this temperature, we're now going to have liquid AB2. Okay, so overall, our phase diagram is going to be very similar to our case 1 system. Okay, if we start at this region over here when we have pure A, okay, and we start moving to the right, okay, so when we move to the right, we're actually increasing the amount of AB2. Okay, so keep in mind that any B that we start adding in this direction, okay, goes towards forming AB2. Okay, so in this case, our phase diagram is going to look like this over here. Okay, so we're going to have our melting curves. Okay, they're going to meet again at a eutectic composition. Okay, and we have a eutectic temperature here. Okay. So the same thing can go over here, okay, on this side of the plot. Okay, so on this side we have pure B, right? As we move towards the left, okay, we're adding more AB2. Okay, so anytime that we start adding more A in our composition, all of that A goes towards the formation of our compound AB2. Okay, so again, it's just going to look like another diagram over here. Okay, so we have our melting curves coming together and we also have a unique eutectic temperature. Okay, so overall, our phase diagram just looks like that we have two case 1 diagrams that are stuck together. So we could also label this diagram with the corresponding phases that would exist at each of the regions. Okay, so of course, above the melting temperatures, we'll have just a homogeneous liquid mixture. So we're going to have a melt that is made up of A plus AB2 or B. Okay, so it just depends on the corresponding composition that we'll have. Okay, but overall, our number of phases is going to be equal to 1, and our corresponding variance is going to be equal to 2. Okay, so we need to specify the temperature and the composition in order to describe the system above the melting temperatures of our diagram. Okay, so moving on to this region over here, okay, so we have again, what's on the side here, we have pure A solid, and we have our bordering side over here, which is our melt. Okay, so we have A solid plus melt, so number of phases is equal to 2, and our variance is just equal to 1. Okay, so in this region over here, we expect that we'll have, okay, so the bordering phase over here, this is our AB2 solid, and our bordering phase over here is our melt. Okay, so we have AB2 solid plus melt. Okay, so same things goes, 2 phases, variance of 1. Okay, so below our eutectic temperature here, we have A solid plus AB2 solid. Okay, so 2 phases, okay, variance of 1. Okay, and same treatment can go in this region over here. Okay, so in this region over here, we have our bordering phase, which is AB2 solid, and our melt. Okay, and in this region over here, we have our bordering phase, which is our B solid and our melt. And over here, we have B solid and AB2. Okay, so this is pretty much straightforward. We were just applying what we know from our case 1 system. Okay, so the only unique part over here is that we have the formation of a compound at a particular composition of A and B. Okay, so in this particular example, we're forming AB2, but we could form other types of compounds of different molar ratios. Okay, so we could even form multiple compounds. Okay, so if we have multiple compounds forming with different ratios, we'll just have a very similar type of phase diagram as well. Okay, so some example systems that follow this type of behavior include our gold and tellurium system and also our aluminum and selenium system. Okay, so overall that is our eutectic reactions. We also have another type of reaction that we could encounter, but it's a little less common than our eutectic reaction. So this is called the peritectic reaction. Okay, so this time we form a so-called incongruently melting compound. Okay, so we'll emphasize what this means a little later on. Okay, but in this particular case, let's say that we also form compound AB2. Okay, so when we say that we have an incongruent melting process, it's not really a melting process, but rather we have a decomposition. Okay, so overall, our compound is actually not very stable. Okay, so the stability of our compound does not extend up until its melting point. So it actually starts to decompose to yield a solid phase and a solution of different composition. Okay, so say that if we have AB2 solid, okay, so at the corresponding so-called melting point, okay, it's not really a melting point though, we form B solid and some melt. Okay, so our composition of AB2, for example, we know this to be 33% A and 67% B. Okay, so when we decompose our compound, however, some of the B in this original composition is going to kind of purify out. Okay, so we expect that the composition of the melt is going to be less than 67% B. Okay, but overall, when we take into account the total composition of the mixture, it's still going to be, of course, 33% A and 67% B. Okay, so let's kind of illustrate how this is going to work with a phase diagram. Okay, so again, with this particular composition, we have the exact composition to completely form just AB2. So just pure AB2 along this line here. Okay, so this is our decomposition temperature. Okay, so just to emphasize what we'll have in this particular region, we'll have a corresponding eutectic point and eutectic temperature. So what's going to be different now if we have a peritectic reaction is what's going to happen over here. Okay, so instead of having a peak over here as what we had previously, we're going to have this type of shape in our phase diagram. So overall, once we reach the so-called melting temperature or decomposition temperature of our AB2 compound, okay, it splits off into 2 phases. Okay, so note here, okay, so what we said earlier was that AB2 solid, this is going to be forming B solid plus a melt. Okay, so typically if we have a congruently melting compound, AB2 solid is just going to form AB2 liquid, but this time it just decomposes into its constituent components. Okay, so we have B solid and A plus B liquid. Okay, so if you want to figure out what happens here in the melting temperature, we draw tie lines, right? Okay, so if we want to figure out the phases here, we draw a tie line towards the bordering phase here. So we have B solid, and we have our bordering phase over here. So this corresponds to a melting curve, right? So this is the melt. Okay, so the composition of this melt over here, we could draw a vertical line downwards. Okay, so note, as we said earlier, okay, the composition of the melt is going to be less than 67% B, because some of that B, okay, ended up forming and decomposing into B solid. Okay, so this is our peritectic reaction. So we could also label the corresponding phases using our technique again. Okay, so of course, above the melting curves, we have our melt. Okay, in this region over here, we have A solid and melt, AB2 solid and melt, A solid and AB2. Okay, so in this particular region over here, so our bordering phase is B solid and our melting curve. So we have B solid and melt. Okay, so in this region over here, we have AB2 solid and B solid. So we expect that our phases here are going to be AB2 solid and B solid. Okay, so overall, this is a very simple example of a peritectic reaction. Okay, so again, you have incongruent melting. Okay, so not really melting. Keep in mind, this is more of a decomposition process. Okay, in which our compound, okay, breaks down into one solid phase and a melt. Okay, so this melt over here, always keep in mind, this is just made up of A plus B in the liquid phase. Okay, so a homogeneous mixture. Okay, so overall, keep in mind that these are just very simple examples of what we may encounter in our phase diagrams. Okay, so some examples of systems that follow our case 2b system include our aluminum and calcium system. Okay, so we also have several ionic compound systems as well. Okay, so overall we just discussed three major types of phase diagrams we might encounter, but keep in mind in more realistic phase diagrams and more complete phase diagrams, we typically encounter more complex systems. Okay, so note over here that we have our aluminum and copper system, and it's usually a composite of the many different cases that we could encounter. Okay, so here we have like a simple eutectic system over here, then you have a lot of peritectic compounds over here, so note that you have the typical shape that we saw earlier. Okay, so overall things can get really complicated once we start considering the phase diagrams of many other compounds. Okay, so as practice, let's try to sketch some diagrams using given information. Okay, so we want to sketch our magnesium and lead phase diagram in terms of mass percent lead given the following. Okay, so this is, okay, so let's investigate what we know over here. So we're given the atomic weights of magnesium and lead. We're also given the melting points of our pure components. And we see here that we form an intermetallic compound over here, okay? And we're also given the corresponding eutectic mixture compositions and their eutectic temperatures. Okay, so the first thing to do here is probably to kind of identify where we could put this compound in our phase diagram. Okay, if we have magnesium to lead, okay, so for this we have 2 magnesium for every lead. Okay, so what we need to do, however, is plot this in terms of mass lead. Okay, so we want to know what percent of lead will this compound be. Okay, so we know that magnesium has an atomic mass of 24.31. Okay, and then lead, on the other hand, this is going to be 207.2. Okay, so this is going to be 48.67, and our original mass over here, 207.2. Okay, so if you want to get the mass ratio, so this is the mass of magnesium per mole of our compound, this is the mass of lead in our compound per mole. Okay, so divide this by the total mass of our compound, so this is 255.82. Okay, this will give us 81% weight by weight lead. Okay, and then this will also give us 19% weight per weight magnesium. magnesium. Okay, so we know where we could plot this compound. It's going to be at 81% lead. Okay, so overall, we know that we form a melting point. We have a melting point of our intermetallic compound. So it's not really a decomposition. Okay, so over here, we know that we form a eutectic reaction. Okay, so our compound is going to be melting congruently. Okay, so let's put this all in a phase diagram. So here we have a graph, okay, so let's label some very important percent masses over here, okay, so our compound that is going to be magnesium 2 lead, that's going to be at 81%, so 1, 2, 3, 4, 5, 6, 7, 8, okay, so we could put our compound here, magnesium 2 lead, okay, in this region over here. Okay, so this is around 81%. Okay, so let's also label our corresponding eutectic compositions. Okay, so this is going to be 64%. So 1, 2, 3, 4, 5, 6. Okay, so this is around 64%. Okay, and then we have 90% lead for our other eutectic composition. Okay, so let's also label the corresponding melting points of our pure compounds. Okay, so on this side we have pure lead, so its melting temperature is 3 to 8 degrees Celsius. Okay, so let's just sketch it over here. Okay, so melting temperature of lead. Okay, and then the melting temperature of magnesium is 648, so it's around here. Okay, so let's also indicate the melting temperatures of our eutectic mixtures. Okay, so for 64% lead, this is going to melt at around 480. Okay, so this is around here. Okay, and then the melting point of the other eutectic mixture is going to melt at 260 degrees. Okay, so that is going to be around here. Okay, so how about the melting point of our intermetallic compound? That's going to be 550, so that is here. Okay, so now that we have these points, we can just put everything together. Okay, so we know that for our intermetallic compound, we have a straight line going down here up until its melting temperature. So this line represents solid and pure magnesium 2 lead. Okay, and then we have the corresponding eutectic temperature. Okay, so here, this is our eutectic temperature. It's not quite straight, but it's fine. Okay, and we know that the melting curves are going to meet at this point here. So melting curve here, melting curve over here. Okay, so it doesn't have to be super pretty. Okay, so we also have our eutectic temperature over here. Okay, and then we have our meeting of our melting curves at this point here. Okay, so this is the general shape of our phase diagram. Okay, so on top here we're going to have our melt. Okay, in this region here. Okay, so this region is going to be, so we're going to have pure magnesium on this side. So we have magnesium solid plus, okay, so the bordering side over here, this is the melt. Okay, so on this side, on the other hand, we're going to have, okay, so the bordering phase is our intermetallic compound and our melt. So this part here is going to be magnesium 2 lead solid plus melt. Okay, in this region over here, we have just magnesium solid plus magnesium 2 lead. And in this region over here, you actually have the same thing here. You have magnesium 2 lead solid plus melt. Okay, this part over here, this is your lead solid plus melt. And this region over here, this represents, okay, so bordering phases, you have lead solid plus magnesium 2 lead solid. Okay, so this is our phase diagram, so it's not very smooth looking, but at least we sketched it out and we're able to label everything. Okay, so overall we just discussed two component systems. Okay, so we looked at two major cases when we have no chemical reaction between the components, and a possible case when we have a chemical reaction between the components as a eutectic reaction or a peritectic reaction. Okay, so now let's look at increasing the number of components in our system. Okay, so let's look at three component systems. Okay, so before we begin, again, let's consider the variance of these types of systems. Okay, so again, our expression for variance is equal to F is equal to 2 plus C minus P, where 2 represents the temperature and the pressure variables. Okay, so since we have a three-component system, C is equal to 3, so that means F is going to be equal to 2 plus 3 minus P. Okay, so in other words, we're going to have F is equal to 5 minus P. Okay, so since we would have at least just one phase, our variance is going to be 4. Okay, so we're going to have a lot of variables to take into account. Okay, so when we're considering three-component systems, okay, in order to reduce the number of variables to investigate in our phase diagrams, we're just going to keep these two variables constant. Okay, so for our three-component system diagrams, we'll be considering a case in which we have constant temperature and constant pressure. Okay, so what we'll just investigate is the effect of composition. Okay, so at constant temperature and pressure conditions, okay, our variance is just going to be equal to 3 minus P. Okay, so this will be a little bit easier to deal with, because we just need to specify our percent composition. Okay, so note, however, that we have three components, right? So we need to specify two components, at least two components, in order to specify the third. Okay, so we're going to need three sort of things to plot on our diagram. So we can't exactly do that with the diagrams that we've dealt with before. So when we're dealing with three-component systems, we'll be using a special kind of diagram called the ternary phase diagram, or the Stokes-Rozeboom diagram. Okay, so this is actually a really cool triangular diagram that has three variables plotted. Okay, so on this axis over here, okay, these ticks represent the percent composition of A. Okay, so on the bottom over here, these ticks on the bottom represent the percent composition C, and on the top over here, this represents the percent composition B. Okay, so note that I added little arrows over here to indicate which of these lines represent the compositions of each of the axes. Okay, so this over here, so if we're dealing with 10% B, this line over here, this straight line here, represents a constant composition of 10% B. Okay, so if we're dealing with 10% A, okay, so this line over here represents a constant composition of 10% A. Okay, so note that the other compositions of C and B may vary. Okay, so along this line here, okay, so again, along this straight line over here, this represents a constant composition of 10% C. Okay, so actually this is a really nice diagram to represent different compositions. Okay, so let's get a little bit of practice in using this type of diagram and how to read it. Okay, so let's try to plot these points over here, and we'll see that if we just specify these 2 points over here, we could automatically specify the composition of the third. Okay, so if we're going to look for 20% A and 40% B, okay, so 20% A, that is around here. Okay, so 20% A, okay, 40% B, that's over here. So we need to find the place where these two things intersect. Okay, so 20% A, this corresponds to this line here. Okay, and then 40% B represents this line over here. Okay, so this is our first point, 1. Okay, so note, let's look at what the composition of C is going to be. Okay, so if we follow these lines here, okay, we see that we have 40% C, as we have 20% A and 40% B, which makes sense because, of course, if we add these compositions together, we get 100%. All right, okay, so let's try this with another example. 60% B, 40% C. Okay, so 60% B, that's over here. 40% C, that is going to be over here. Okay, so that means our point 2 is over here. Okay, so note that since we have 60% B and 40% C, we have 0 A. Okay, which makes sense because we're on this borderline over here. Okay, so note that if ever we have points that are plotted along the edge of our triangle, okay, we're going to have 0% of one component, which is not going to be along this line. Okay, so note here, along this this vertex here represents when we have 100% C. This vertex over here represents when we have 100% B. Okay, so along this edge over here, we're just varying the composition of B and C and have 0% A. Okay, so overall, this tells us we have 0% A. Okay, so next couple of examples. Okay, so 50% A. Okay, so that is over here, 50% A. Okay, 20% C. 20% C is over here. So if we trace this, 50 and 20, this is over here. Okay, so we can figure out the corresponding percent composition of B. So that should be 30%. Okay, so this is going to have 30% B. Okay, so last example, let's check out 10% C, 5% B. Okay, so 10% C, this is right over here. Okay, so 5% B. Okay, so 5% B is going to be represented here. Okay, so 5%. Okay, so if we follow along here, it's going to be half this. Oh, here. Okay, so 10%, 5% B. Okay, the corresponding composition of A is going to be over here. So you might need to draw some lines. Okay, so this is going to be 85% A. Okay, so this makes sense. Okay, so 85 plus 5 plus 10, that is 100%. Okay, so hopefully it's kind of clear how you could use the Stokes-Rozeboom diagram in order to describe the composition of your system. Okay, so we'll get a lot of other practice in using this diagram once you start applying this with our different types of systems. So the systems that we'll be discussing for 3-component systems include our liquid, liquid, liquid systems. Okay, so that means all of our components are in the liquid phase. Okay, so we have several cases. Okay, so we could have 1 binodal curve, 2 binodal curves, 3 binodal curves. So this just relates to how our liquids are going to be miscible with one another. Okay, so we'll talk about this later on. Okay, so our second set of cases include our solid, solid, liquid systems. Okay, so for case 1, we're just going to consider when only the pure components crystallize from solution, and for the second case, we could have, similar to our 2-component systems, a reaction between our components. Okay, so let's look at our first liquid, liquid, liquid system. Okay, so this is when we have case 1, when all components are completely miscible, except with one partially miscible pair, which we'll consider to be A and C. Okay, so in this particular case, B is going to be miscible in both A and C, but A and C are just partially miscible with one another. Okay, so that means they have limited solubility in one another. Okay, so when we construct our phase diagram, let's focus first on this particular region, on this edge of our diagram here. Okay, so this is when we still don't have any B that is in our mixture. Okay, so we're just going to be varying the amount of A and the amount of C in our mixture. Okay, so if we just have A and C, they're going to be partially miscible in one another, right? So if we're in this part of the diagram here, that means we have very small amounts of C and large amounts of A. Okay, so in this particular region, A can act as a solvent and C acts as the solute. Okay, so that means we could represent a solubility of C in A. Okay, so let's say that it's in this particular composition. Okay, so in this particular composition, we have 10% of C and 90% of A. Okay, so if we're in this part over here, okay, we're below the solubility limit of C, we expect to have a homogeneous liquid mixture because they're soluble in one another. Okay, so once we hit the solubility of C, however, that's when we expect to see 2 phases. Okay, so C is going to start to separate from A because you have a lot of C now that won't be able to interact nicely with A anymore to form your homogeneous mixture. Okay, so the same thing can go once we're in this region over here. Okay, so when we're in this side of the plot, okay, we have a high amount of C, but this time we have a low amount of A. Okay, so in this region over here, C is considered to be the solvent, whereas A is considered to be the solute. Okay, so we could indicate a corresponding solubility of A in C as the solvent. Okay, so in this particular case, for illustrative purposes, let's say that at 80% C and 20% A, this represents the solubility limit of A and C. Okay, so again, in this particular region over here, you expect to see just one phase, okay, so a homogeneous mixture. Same thing goes for over here. You expect to see just one phase, a homogeneous solution of C and A. Okay, here you expect to see a homogeneous solution of A and C. Okay, once you're in between, however, okay, you start to mix large amounts of A and C with one another, okay, so their relative amounts start to become comparable, okay, so that means you start forming layers now, okay, so you expect to see two layers here, okay, so once you start adding B, however, okay, so note on a molecular basis, B can interact appropriately with A and C, okay, so it has favorable interactions with these two components, okay, so if you start adding B in our mixture over here, okay, B sort of acts as the intermediary between A and C, okay, so we could introduce favorable interactions between A and C, okay, so if we start to increase the amount of B, okay, we expect to have this sort of curve over here, okay, so this line over here, this represents the borderline when we see just one phase versus two phases, okay? So let's label the number of phases and the variance in these regions over here. Okay, so above this region over here, you have a lot of B, right? So it pretty much allows our A and C, which are usually partially miscible, to start interacting with one another favorably, okay? So overall, you just have one single phase, and our variance in this case is going to be 3 minus 1, so 2. Okay, so this is consistent with our analysis over here. We just have a single phase over here, single phase over here, so that's extended towards this entire region. Okay, so once we're inside here, we said that we're going to expect to have two layers of liquid. Okay, so we're going to have two phases. Okay, so here we have two phases, so therefore our variance is equal to 3 minus 2, so just 1. Okay, so to give you guys a picture of what's happening here exactly, okay, so here you have a homogeneous mixture of both A, B, and C, and within this curve over here, this is the binodal curve, okay, we're going to have a C-rich layer, okay, so overall you have A and B that is dissolved in C, okay, and then you also have a so-called A-rich layer. So in this particular case, you have high amounts of A, so A acts as a solvent, and you have C and B dissolved in A. Okay, so the next question is, how can we determine the composition of the system within this region over here? Okay, so how do we know the composition of the C-rich layer, and how do we know the composition of the A-rich layer? Okay, so similar to what we had in our two-component phase diagrams, we could determine the composition of the phases using tie lines. Okay, so we could also construct tie lines in this region over here. Okay, but note that the tie lines here, they're not going to be perfectly parallel, but they're going to be sloping. Okay, so actually these tie lines are going to be experimentally determined. Okay, so our tie lines are going to be as follows. Okay, so we have a bunch of lines, okay, that are not parallel to one another, and ultimately they're actually going to meet at a certain point over here, and this point over here is called your plate point. Okay, so overall we could say that the compositions along this region over here, okay, on the left side of our plate point, this represents the composition of our A-rich layer. Okay, and then regions on the right side of the plate point, this corresponds to the C-rich layer. Okay, so this is a C-rich layer because in these compositions, you have a higher amount of C compared to A. Okay, so same thing goes over here. You have a higher amount of A compared to C. So A acts as a solvent here, C acts as a solvent here. Okay, so overall, if ever you're within this region here, okay, our solution splits off into two parts, okay, the A-rich layer and the C-rich layer. Okay, so for example, we're along this plate point over here, okay, so whichever composition that we have, just as long as it's along this tie line, so say that we have a mixture that is 20% C, 70% A, and 10% B, okay, the composition of our A-rich and the C-rich layers are going to be, okay, so the A-rich layer is going to be 79% A, 12% C, 11% B, and the composition of the C-rich layer is going to be as follows: 23% A, 57% C, 20% B. Okay, so just so long as you're along this tie line, you're going to have a constant composition of A-rich layer and C-rich layer. Okay, so for example, we said earlier that if we have this system over here, okay, it's going to split off into two layers: A-rich layer, C-rich layer. Okay, so if, however, you have a composition of our original solution as this over here, okay, we're still along the same tie line, so that means our solution is still going to have the same phases, okay? So even though you have this composition of the C-rich layer is going to be constant, and the composition of the A-rich layer is going to be constant as well, okay? But note, however, that the distribution of the entire solution with respect to each layer is going to be different. Okay, but overall the compositions are going to be the same. So what's important about the plate point as well is that note that as we go along the tie lines, okay, the tie lines start to converge at our plate point, right? And note that the compositions of the A-rich and the C-rich layers become closer and closer to one another. Okay, so the importance of the plate point is that the plate point represents when the composition of the A-rich layer and the composition of the C-rich layer become equivalent. Okay, so this becomes the point when we see a disappearance between the boundary line of our A-rich layer and our C-rich layer, and this is the point where we ultimately have just a single phase of our entire mixture. Okay, so note, guys, that again, our tie lines are not going to be parallel to one another, but actually if you extend these lines, okay, they actually converge to a single point over here. This point of convergence, this is called the delta point. Okay, so the delta points helps in constructing these tie lines with experimental data. Okay, and it also helps with approximating where the plate point could be. Okay, so additional points as well, guys, is that the position of the plate point could also assist us in determining in which phase our B component is more soluble. Okay, so let's recall the compositions of our layers again. Okay, so the C-rich layer has more B, right? Whereas the A-rich layer has less B. Okay, so that means that B is preferentially distributed more towards the C-rich layer. Okay, so therefore B is more soluble in C. Okay, so note that the position of the plate point is actually closer to the A-rich layer. Okay, this means that since you have a larger region here for the C-rich layer that corresponds to B compositions, B tends to dissolve more in the C-rich layer. Okay, so we could also extend this treatment when we have our case 2, so this time we have two binodal curves, okay, but keep in mind that the same principles still hold with our case 1. So this time we have two partially miscible pairs and one completely miscible pair, which is A and C. Okay, so in this case, A and B are just partially miscible with one another, so we have corresponding solubilities of A in B and B in A, and we also have partial miscibility between C and B. Okay, so when labeling this, of course, in this region over here, we have just one phase, and inside these regions, you have two phases. Okay, so here we have our corresponding plate points. Okay, so that means that this composition over here, this represents the B-rich layer. Okay, these compositions over here represent the A-rich layer. Okay, so for this binodal curve, on the other hand, this part over here, okay, this represents again the B-rich layer, and this composition again represents the C-rich layer. Okay, so interesting things happen once we start changing the temperature. Okay, so if we decrease the temperature, the tendency is that you also decrease miscibility. Okay, so if we decrease the temperature, we actually have a merging of our binodal curves. Okay, so this part over here, this represents a single phase, and this region over here with our tie lines, this represents two phases. Okay, so what are our two phases? Okay, so this line over here, this represents a B-rich layer. Okay, so we have A and C dissolved in our B-rich layer. Okay, so B here acts as a solvent. Okay, so along this line, however, okay, so note that A and C are completely miscible with one another, right? Okay, so these particular compositions, this represents an A and C-rich layer. Okay, so B is dissolved in this particular solvent here, A and C. Okay, so of course, since we have two binodal curves, our third case is when we have three binodal curves. Okay, so ultimately all of our components are just partially miscible with one another. Okay, so you could also identify based on the positions of the plate points which regions represent an A-rich layer, a C-rich layer, or a B-rich layer. Okay, so also a very interesting thing happens when we decrease the temperature over here. So again, decreasing the temperature leads to a decrease in miscibility. So ultimately, all of these curves are going to start merging with one another, okay? So upon decreased miscibility, we have this type of phase diagram that starts to appear. Okay, so actually, this is a very, very interesting case because of what happens inside this triangle over here. Okay, so let's blow this up and analyze this further, okay? So note over here that what happens here is that you start to have a merging of our curves here. So this represents a constant composition in which A and C are dissolved in B. Okay, so you have a maximum solubility of both A and C in B. Okay, so this solubility then is going to be fixed. Okay, so you can only dissolve so much A and C in B after all. Okay, so the same thing goes over here. This composition here, this represents B and C dissolved in A. Okay, so maximum solubility is observed over here, and this over here, this represents A and B dissolved in C. Okay, so note that all of our solvents are just partially miscible with one another. Okay, so they will have a tendency to form layers. Okay, so inside this region, you actually have three phases, and those phases are your solution of A, your solution of B, and your solution of C. Okay, so this is super interesting because you have this sort of picture that happens here. Okay, so you have your C-rich layer, B-rich layer, and A-rich layer. Okay, so note that the layering is going to depend on the densities of the solvents, but just note that for this particular system, you're going to expect to see three layers of liquid. Okay, so therefore three phases. Okay, so the number of phases here is 3, so the corresponding variance is going to be equal to 0. Okay, so that means this region here is invariant. So regardless of your composition within this region, you're always going to have a fixed type of system. Okay, so you're always going to have the same distribution of the solution within these layers. Okay, so if ever you happen to just add more of one component, the one component is just going to distribute itself within the constant composition of these layers here. Okay, so super cool, right? So an example of this type of system is actually with succinyl nitrile, water, and ether system. Okay, so if you just so happen to have these types of compounds in your lab, you might want to test it out and observe the 3 layers here. Okay, so overall, these represent the types of liquid systems that we might encounter. Okay, so keep in mind again that these are just example systems, so there's many different types of possible cases for liquid systems. Okay, so now let's look at our second type of third component system, which is when we have solid liquid systems. Okay, so for our discussion, we'll be focusing on aqueous solutions. Okay, so our liquid component in our system is going to be water. Okay, so we're just going to be investigating the solubility behavior of two components, okay, in an aqueous solution. Okay, so first and foremost, let's start off with this particular example. We only have pure components crystallizing from solution. Okay, so similar to our two component system, in this particular case, we have no chemical reactions between our pure components. Okay, so if we focus on this edge of our triangle over here, we're just going to be looking at the behavior of how a solid can dissolve in water, okay? So let's allow this little tick over here to represent the maximum solubility of A in water, okay? So if we are above the solubility limit, we expect to see that we're going to have a saturated solution of A, and we also expect to see some solid A as well, okay? So below the solubility, we're also going to expect to have an unsaturated solution. So same thing goes for this borderline over here if we just have B and water in our system, okay? So this line over here represents the solubility limit of B, okay? So if we are below the solubility limit of B, okay, so note that we have very low B and very high amounts of water, okay, we're going to have an unsaturated solution. But once we go beyond this limit over here, okay, we expect to have a saturated solution of B, and we also expect to see some B solid, okay, that remains undissolved, okay? So if we put these two things together, okay, so this is when we have pure A, right? Okay, so if we start to add some B to our mix, okay, we're going to have a solubility curve, okay, that's going to change as B is added to our solution, okay? So we're going to have a solubility curve over here, okay? This is a solubility curve for A, and we also have a corresponding solubility curve for B, okay? So these two curves are actually going to meet at a point over here, okay? So at this point, we expect to have a saturated solution in both A and B, okay? So to complete our diagram, we draw a straight line from this point to this point and this point to this point, okay? So overall, this is our phase diagram for our water system that has A and B solid components, okay? So now let's investigate how we could label our diagram here, okay? So consistent to what we said earlier, okay, so if we have high amounts of water, okay, and we are below the solubility limits of our solid components, overall, we expect to have an unsaturated solution over here, okay? So we have a single phase, therefore our variance is going to be equal to 2. Okay, so now let's focus our attention to this region over here. Okay, so in this region, we are now beyond the solubility limit of A, but note that we haven't yet achieved the maximum solubility limit for B. Okay, so therefore within this region, we expect to have A solid, a saturated solution of A, but our solution is still going to be unsaturated in B. Okay, so overall the number of phases that we expect to see in this region over here is our solid A and our solution over here. Okay, so we have P is equal to 2, therefore our variance is equal to 1. Okay, so note that along this barrier here, this line over here, the solubility line of A, this is when we start to see the saturated solution of A forming. Okay, so we now have an equilibrium between solid A and the saturated solution of A. Okay, so same treatment can go for this region over here. Okay, so note that for sort of cone-like regions in our ternary diagrams, okay, the phases present can be determined based on the vertices, okay, and any curved borders here, okay? So in this particular region, our vertex over here is going to be solid B, pure B, okay? And then the bordering curve over here, this is going to be our solubility limit for B, okay? So therefore, we expect to see a saturated solution in B and some B solid, okay? Note, however, that we have not yet achieved the saturating limit for A. So therefore, our solution here is unsaturated in A, okay? But we have two phases because B solid here starts to form, okay? Because we achieve the saturating limit of B. Okay, so note here that we have the meeting of our solubility limits of A and B, right? Okay, so that means that this particular point over here, this represents the point when we have a solution that is saturated now in both A and B. Okay, so since we have a saturated solution, okay, our system is now going to be in equilibrium between dissolving a solid A and both solid B and precipitating it out of solution. Okay, so therefore this point represents a saturated solution in A and B. Okay, so the number of phases is actually equal to 3 because we have our saturated solution in A and B as well as some traces of A solid and B solid. Okay, so actually this point is an invariant point because our variance is equal to 3 minus the number of phases, which in this case is 3. Okay, so this point here, this is defined for our system. Okay, so this represents, again, both the solubility limits of both A and B. Okay, so if you want to label the phases present in this region, on the other hand, okay, so if you have a triangle shape within a ternary phase diagram, the phases present here will be represented by the vertices of the triangle. Okay, so here we have solid A, solid B, and our saturated solution in A and B. Okay, so again, the number of phases is equal to 3, and the corresponding variance is equal to 0. Okay, so that means the system here, okay, regardless of where you are in this region over here, you're going to have the same composition of our system. You're just going to have A solid, B solid, and the saturated solution in A and B. So additional things to note here as well is that since we have both a solid A and a saturated solution in A, the distribution of A between the phases can also be described using tie lines. Okay, so here we have our tie lines for our cone-shaped regions here. Okay, so actually to give you guys a better picture as to what's happening in this phase diagram, okay, we could use a hydration line. Okay, so a hydration line represents what happens if we start with just solid A and solid B and we start adding water. Okay, so say that we start with this particular point over here at 70% A and 30% B. Okay, so this is represented by our beaker over here, so we just have 2 solids, right, and 0 water. Okay, so our hydration line follows this line over here. Okay, so as we go up this line here, we're just increasing the amount of water in our system. Okay, so we're just going to be investigating what happens when we add water to our 2 solids here, which are soluble in water. Okay, so you'll see as we discuss this, the events described by this phase diagram is very familiar to you guys in real life experience, say in your laboratory experience. Okay, so overall, if we add water to this system over here, say that we go up along this line here, okay, we know that we're pretty much just going to form a saturated solution in A and B. So the water that we add here is going to dissolve some of our solid. Okay, but note that we have a lot of our solid present and we don't have enough water yet to completely dissolve our A and B. Okay, so overall, the concentration of A and B in the solution is going to be fixed. Okay, so the concentration of A and B is just going to be dictated by the solubility of A and B in water. Okay, so if we increase the amount of water, okay, so we still are within this region, right? Okay, so we still have solid A, we still have solid B, and we still have the same saturated solution in A and B. Okay, so that's why this whole region here is invariant, because the nature of the phases don't really change. Okay, so you still have the same exact saturated solution with a fixed concentration of A and B that's dictated by these solubilities of A and B in water. And you also still have solid A and solid B. Okay, so what just changes here, however, is the distribution of the entire mixture within these phases. Okay, so note that some of the A went into the solution and some of the B went into the solution because we added more water. Okay, but overall, you still have the same things in your system. Okay, so once we hit this line over here, this represents the point where we can completely dissolve our B. So we've reached the solubility limit of B, but we have not yet reached the solubility limit of A. Okay, so we add enough water to completely dissolve B, but not enough to dissolve A. Okay, so we're now along this region over here. So this is just the point when we start to dissolve B. So we might have some traces of B in equilibrium with our saturated solution of B. Okay, so once we go beyond this line over here, okay, so we're now within our cone region. Okay, so again, we still have a saturated solution in A, okay, but now we have an unsaturated solution in B. So we have enough water to make our solution unsaturated in B. Okay, so note that since we're still within this region here, we still have solid A. Okay, so once, however, we hit this line over here, okay, so we just hit the saturation line of A, okay, so our solution is, again, still unsaturated in B, okay, but it is still saturated in A, okay, so you still might see some traces of solid in equilibrium with the saturated solution in A. Okay, so once we add even more water, okay, so this is the point where we have a completely unsaturated solution now. We have gone beyond the solubility limit of A and B now, so overall we have a homogeneous solution which is now unsaturated in both A and B. Okay? Okay, so this is for our first case when our pure components just crystallize from solution. Okay, so we could also do the same analysis for when we have a reaction between our components. Okay, so but keep in mind again that the same analysis, the same treatment for our phase diagram is going to be the same. We're just going to be adding an additional feature to our phase diagram. Okay, so for our second case, let's consider when our pure components react to form a binary compound. Okay, so this is very similar to our two component system in which our two components reacted to form a binary compound. So in our particular example, let's consider hydrate formation. Okay, so we're going to have one of our pure components, A, reacting with water to form the hydrate. Okay, so also in our phase diagram, let's also plot our composition in terms of weight percents. Okay, so before we begin, let's also consider where we could plot this composition over here, the hydrate composition. Okay, so overall we know that for every mole of A, we have 2 moles of water in our hydrate, right? So if ever we have this exact composition, we know that we're going to have a hydrate formation. Okay, so overall 1 mole of A is 164 grams, whereas 2 moles of water is going to be 2 times 18. Okay, so 2 times 18, that is 36. Okay, so overall, if we get the total mass of our hydrate, that is going to be 200. Okay, so if we get the percentage of this, 164 grams of A over the mass of the entire hydrate, that is going to be times 100%, 82%. Okay, so for water, this is going to be 18%. Okay, so overall we could plot our hydrate on this part of our graph over here, 82% A. So this corresponds to 18% water as specified. So overall we could label this particular composition as our hydrate. Okay, so to complete our phase diagram, okay, so we could connect this point over here with our other region here. So we draw a line from here to here to here. Okay, so we have this triangular region. Okay, and then the rest of our phase diagram follows the pattern that we had in our previous case. Okay, so we just have our solubility line here, okay, our other solubility line here, and the joining of those curves over here. Okay, so again, let's label all of these regions. Okay, so over here we know that we have an unsaturated solution because we have lots of water. Okay, and then we haven't reached the solubility limits of our compounds. Okay, so in this region now, okay, so again, as we mentioned before, when we're determining the phases within a cone region in a phase diagram here, we have to look at the vertex of the cone and the borderline of the cone. Okay, so overall our solid here is going to be our hydrate, and it's going to be saturated in the hydrate and unsaturated in the other component B. Okay, so the same analysis can also be done for the other region over here. We know that this is B solid, and we're saturated in B and we're unsaturated in A. Okay, so this point over here, this represents when we have a saturated solution in A hydrate and B. Okay, so keep in mind that we also have some solid forming in this part over here. So we now have an equilibrium process. Okay, so within this triangle here, okay, so again, recall what we said about determining the phases present in a triangular region in a ternary phase diagram. We look at the vertices. On this vertex, we have our saturated solution in 2 of our components. Okay, we have our hydrate and we have our B solid. Okay, so overall, saturated solution in A hydrate and B. We have our A hydrate solid and our B solid. Okay, so again, the number of phases is 3, so overall the variance is also equal to 0. Okay, so in this new region over here, okay, so again, it's a triangular region, so we could just indicate the phases present by specifying the vertices in the triangle. Okay, so in this triangle, we have A solid, B solid, and the A hydrate solid. Okay, so again, we have 3 phases. Okay, so our variance again is equal to 0. Okay, so to give you guys a better picture again of what's happening exactly in this phase diagram, we could also do the same analysis as what we did earlier. We could do a hydration line, okay? So again, let's start with the same composition that we began with before. So we have 30% B and 70% A, okay? So we're going to be hydrating our solid. We're going to be adding water to this original amount of A and B, and we're going to see what's going to happen based on what we could see here on the phase diagram. Okay, so again, we have our beaker full of just pure A solid and B solid. Okay, so when we add water, okay, so what's going to be different this time is that we know that A reacts with water to form a hydrate. Okay, so that means that any water that starts to appear here, just so long as we're within this region, all of that water goes towards forming a hydrate. So if we add water, okay, that water reacts with A in order to form our hydrate. Okay, so overall, if we're still within this region and we add enough water, okay, that additional water, again, is just going to react with A to form more hydrate. Okay, so it's going to continue until we hit this line here. Okay, so if we're all along lines here, we could determine the phases present in this region by looking at the points at which it intersects. Okay, so we have B solid and we have our A hydrate. Okay, so that means that in our system, all of our A is now in the hydrate form, and we also have B present in our system. Okay, so once we start adding more water, that's when the additional water could start dissolving some of our solids now. Okay, so upon adding water, okay, we now have a saturated solution in our two components. Okay, so note here that we wrote our solution as being saturated in the hydrate. Okay, so based on experience, you guys know that this dissociates later on into just A aqueous and just water. Okay, but for the sake of formality, we could write down the solution as saturated in this particular component over here. Okay, because it's not always going to be a hydrate that we know dissolves further. Okay, so for the sake of formality, we'll be writing it as the hydrate in aqueous form. Okay, so overall we have a saturated solution in the hydrate and B, and we still have our solids present. So again, if we add more water until we reach this line over here, okay, we have a saturated solution in both our two components here in A hydrate and B, but we still have some A hydrate solid present. Okay, so if we move forward and add more water, okay, so we're going to add more water so that we can make our solution now unsaturated in B. Okay, but we still have a saturated solution in our A hydrate and we still have some A solid present. Okay, that is until we reach this saturating line over here. Okay, so this is a saturation line of A hydrate. Okay, so at this point now, okay, you have your saturated solution. Okay, so our solution is in equilibrium between precipitating and dissolving in our A hydrate. Okay, so adding even more water, okay, allows us to go beyond the saturating line of A hydrate. So overall, we now have an unsaturated solution. Okay, so overall, we're just following what happens even intuitively when we add water. Okay, so the phase diagram just allows us to kind of formalize and represent the events that occur in our solution once we change the composition of our system. Okay, so hopefully you're able to relate what you know happens in the lab, for example, with this phase diagram that we constructed here. Okay, let's try out an example here. Okay, so let's just very quickly sketch and label the mole percent phase diagram of our barium hydroxide, sodium hydroxide, water phase diagram. So based on this, we know that barium hydroxide forms a hydrate with water, and we also know that barium hydroxide is less soluble than sodium hydroxide. Okay, so let's just quickly sketch this out. So before we start, let's figure out where we could draw this point over here, okay, our hydrate. So in our particular phase diagram, we have our barium hydroxide on this part of our ternary phase diagram. Okay, so let's look for the mole percent in which we could indicate this compound over here. Okay, so we know that we have 1 mole of barium hydroxide for every 3 moles of water. Okay, so the total number of moles then is 4 moles. So therefore, at 25% barium hydroxide, okay, and at 75% mole water, this is when we have our barium hydroxide hydrate. Okay, so let's look for that over here. Okay, so at 25% barium hydroxide and 75% water. Okay, so 75% water is all the way over here. Okay, this represents the region in which we could have our barium hydroxide hydrate. Okay, so similar to what we did earlier, okay, so we could connect this point with this point over here, and we now have our region, our triangular region, in which we expect to see just our barium hydroxide hydrate, okay, solid, okay, our barium hydroxide solid, okay, non-hydrate, and our sodium hydroxide. Okay, so the rest of this diagram will be very similar to our case 1 diagram again. So we'll just be adding solubility curves here and then connecting them into cones. Okay, so what we know here is that barium hydroxide is less soluble than sodium hydroxide. Okay, so that means more sodium can dissolve in water. Okay, so we could approximate our solubility of sodium hydroxide to be, say, over here. Okay, so let's say that we have like 20% of sodium hydroxide forming a saturated solution now. Okay, so if we know that barium hydroxide is less soluble than sodium hydroxide, so that means less barium hydroxide will form a saturated solution already. Okay, so let's say that 10% with 90% water is going to form a saturated solution. Okay, so overall, this is going to be our saturation point for barium hydroxide. Okay, so it's just a qualitative measure. We just want to make sure that this point is going to be higher than this point over here. Okay, so if we connect these, okay, so let's make some solubility curves over here. So it's just a sketch. Okay, so we have a intersecting point over here. So this represents our saturated solution in both sodium hydroxide and barium hydroxide. So let's just connect this with our points here. Okay, so this pretty much completes our phase diagram now. Okay, so up here we have our unsaturated solution. Okay, so inside here we have our hydrate, our solid hydrate, plus our saturated solution in this barium hydroxide hydrate, plus unsaturated in our sodium hydroxide. Okay, so same thing goes over here. We have sodium hydroxide solid plus a solution that is saturated in sodium hydroxide. Okay, saturated solution in sodium hydroxide, and this is going to be unsaturated in our hydrate. Okay, this region on the other hand, this is going to be a mixture of barium hydroxide hydrate solid plus sodium hydroxide solid plus the saturated solution in both barium hydroxide hydrate and sodium hydroxide solid. Okay, so overall this is our sketch of our phase diagram. Okay, so hopefully sketching out ternary phase diagrams are clear to you guys now and you know how to interpret them. Okay, so next up we'll be discussing equilibrium in binary liquid mixtures. Okay, so we'll consider liquid mixtures that are completely miscible with one another, partially miscible, and completely immiscible with one another. Okay, and we'll look at their liquid vapor equilibrium this time. Okay, so after that we'll also look at, very quickly, some colligative properties. Okay.